Syzygy, episode 103, Red Dwarf Paradox. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, and I'm sitting in the office of Dr. Emily Brunsden here at the University of York. Emily, how you doing?
Hello. I'm doing well, thank you.
Good. So, this week we're going to be talking about red dwarf stars, which sound like this is one of those things in astronomy, which to me always sounds like it's a dwarf. It's red. So it's not as hot as other stars, and it's smaller than other stars because it's a dwarf star. So presumably they're quite benign and, really, really easy things to deal with. But I get the sense that that's not the case, Emily.
No, and I think we're going to be finding out that these things are actually nasty little stars.
Yeah, and there's been some research this week that's been looking into how nasty those stars are. What's been going on? What are we talking about today?
Well, I think overall today I'm going to present to you the paradox.
The paradox. We like a good paradox.
Yeah. I'm gonna copyright this and call it the Red Dwarf Paradox.
Oh, so this is the Brunsden paradox?
Well, maybe. Actually, probably loads of people have already calling this the Red Dwarf Paradox or some version of a paradox, but it's certainly what I think of as a pretty important paradox.
Cool.
For us to look into.
So we'll do that. And we do like a good paradox on this show because last week we had galaxies which broke the universe. Apparently, they were the wrong size and the wrong age for the wrong time of the universe, and we worked our way through that one. So this time we're going to be looking at your red dwarfs. Sounds good.
Yeah. So in brief, the paradox that we're looking at is that we're looking for exoplanets, right? And we're looking for habitable exoplanets. That's kind of the holy grail of exoplanet science. We want to find things which at least humans, if not humans, could live on. That's kind of a different question in some ways. But planets that life could arise on, to answer arguably the biggest question is there other life in the universe?
Yeah, I mean, that's one of the big ones, right?
Yeah.
In terms of big questions, that's right up there. And we've already answered the question, which is, are there other planets? Like that happened quite a long time ago. We now have a long, long list of exoplanets. We're up into the many, many thousands now. Mm-hmm. So that one's done.
Yeah.
That one's dusted, and lots of different kinds. So now it's, but what's on those planets?
Yeah.
Is there anything out there?
So could life arise on any of these planets? And so that was what we could look at as a habitable planet.
Sure.
Now, quick aside here, we're talking about life as we know it. So life as it kind of seems to have arisen on Earth based on all the kind of principles, water, nice temperature, blah, blah, blah.
Carbon-based life forms. Like it's what we've got. That's the only one. We got an N of one.
Yeah, maybe there are other possibilities, but let's park that aside. We're looking for the easy targets. We're looking for places, planets where life could arise and exist as we understand life to exist on planet Earth.
Sure. If you're going to go and look for life, look for signs of things that you already know. It makes sense. Okay, but why? What's that got to do with red dwarfs? Why do we...
Okay, so we want to find the habitable planets, right?
Yep.
So you would say, okay, let's go look at planets that are similar to the Earth going around the sun. Find some more stars like the sun, find some more planets like the Earth going around the sun. That would be the easiest thing to do, right?
Okay.
Yeah. How long does it take the Earth to go around the sun?
1 year by definition.
Yeah. And the Earth's pretty small and reasonably far away from the sun.
Sure.
So if we want to go find Earth-like planets around sun-like stars, first of all, we need to have amazing capabilities of detection to pick up something quite small, quite far away from its host star. Sure. Which we're only just fringing on being able to do that, really, at the moment.
So you're saying the majority of stars, most of the stars we've seen, most of the exoplanets we've seen are closer?
Yes.
Right.
Yeah. So there's two things happening here. So the first thing is the precision that you've got with your instruments. So remember that all exoplanets we don't look at by looking at a star and saying, hey, are there any planets next to it? That would be nice.
That'd be the easy way.
That's not how we do it. We look at the star itself and look for any changes on the star that indicate that a planet might be going around it.
Right. We're looking at the light from the star and going, hang on, that just dipped or changed in some way. The only way, or the most likely way, that could have happened is a planet went in front of it or something like that.
Yeah, exactly.
Yeah, so you're inferring.
Yeah. Yeah. So we need to look at the stars.
Yep.
So let's say we go and look at lots of stars that are like the sun. Now, as I say, the first thing you need to know is the precision to be able to pick up something as small as the Earth, which we're only just getting to really in our techniques. So that's pretty hard. The second thing is you need to have the patience to wait several years, right? Because you want to pick up 2 or 3 orbits at least to be sure.
Yeah. Because, I mean, if it just whooshes past once, great. What was that? Was that what we thought it was? Well, let's wait for it to come around again. But, as you said, we take a year to do that. Other planets, slightly more, slightly less.
Yeah, so finding exact copies of our particular system is tricky and
it's going to
requires
take
a lot
while.
of patience.
Yeah,
exactly. So instead, what you might say, well, let's go and play with the statistics, right? So actually, sun-like stars are not the most common type of stars in our galaxy.
Okay.
We're kind of in the middle of the road in terms of frequency of occurrence, or how many stars like the sun are the kind of a medium number are existing in our galaxy. But let's go to the type of stars where you've got loads of that particular type, and those stars are anything that's smaller than the sun. Basically, the smaller you go, then the more of them there are. And these are what we call red dwarf stars.
Okay.
So they're stars like the sun. They're very similar. You could get very confused in the terminology quite quickly if you weren't paying attention, because we have other types of stars that sound similar. We have red giant stars, for example.
Right, yeah, giant versus dwarf. There's obviously a difference.
Red giant's
there.
Completely different thing. We'll talked about them a minute before, and we'll park those again. White dwarfs, also completely different thing, nothing to do with what we're talking about today. Black dwarfs, different thing. Brown dwarfs, different thing.
Okay.
Right.
All right. But
We're red
dwarfs today.
Yeah.
And the redness is all about temperature.
Yes,
right?
yeah. So these are stars that are smaller than the sun and therefore cooler than the sun, because they don't have the rate of fusion that our sun has. So they're fusing hydrogen slower, which means that their surface temperatures end up being smaller, so they look redder.
Right. Okay. And presumably that's because they are smaller, there's less mass, there's less pressure down on the core from the gravitational, pull of all of that mass, which means the conditions in the core are not as extreme. So you're not getting crazy amounts of fusion happening.
Yeah.
It's just happening at a slower pace.
Exactly. Cool. Yeah. So that's quite cool. But there's loads of them. So that's great. There's loads and loads of them. The most common types of stars, and particularly what we call M dwarfs. So things that you if you talk about the sun has a surface temperature of kind of 5,800-ish Kelvin or Celsius. It's kind of the same at that point. So we're looking at stars that are more kind of in the 3,000s, 3,500. So a bit cooler.
Definitely down in the redder end. Yeah.
But the good news is there's loads of them, so we can study loads of them. The bad news is they're not so bright, but that's we'll park that one again. We just need bigger telescopes to see them then.
Sure. Put in the budget proposal.
Right, most common. Now, the wonderful thing that comes with that is because these stars are cooler, it means that the distance which a planet has to orbit in order to be at a similar temperature to the Earth is much smaller.
Right. So if we're talking about what they call the habitable zone, right, which is, distance away from stars so that you're not catching fire. You're not so close that it's really, really hot. You're not far enough away that it's really cold all the time. You're in this nice little Goldilocks zone in the middle there. And if the star's cooler, then that's closer to the star, that zone. And if that's closer to the star, then that means the orbit's shorter.
Yeah.
Which means we can see more of them.
So they're easier to detect.
Excellent.
So that's great. So we've got these planets that are snuggled in closer to the star, makes them easier to detect. They might only have orbits that take a month, something like that. So, it's nice. It's much easier to go and observe these.
Which means you can collect over a period of time. You can collect more data about those if the planet goes in front of the star, you can see those dips in the light curve more often. You can get more data. You can get more information about what's going on around that star, which gives you much more precision in your interpretation.
Yeah. So they're great. They're great. The third thing that's really great about these these red dwarf stars is that they hang around for ages. So the sun, we're about halfway through the sun's what we call main sequence lifetime, or its main hydrogen fusing part of its life. It's been doing this hydrogen fusion for kind of 4.5-ish billion years. It's got another 4.5 billion years to go.
Okay, which sounds like a really long time, but the sun's burning through, as you said, it's sort of a somewhere in the middle. It's a moderate kind of size star, and the bigger you are, the shorter your life is? Is
yes,
that how that works?
Yes, it works. Yeah, because you're fusing through your fuel much faster.
Right. You're hotter, you live faster, you die younger.
Yeah.
Which conversely means presumably red dwarfs last like forever.
Yeah, exactly. So while the sun will last for overall its lifetime is kind of around about 10 billion years, we can talk about tens of billions of years, 20, 30, 100 billion years potentially for these red, I keep saying white dwarfs. For these
You've done
red
it to
dwarfs.
yourself now.
Yeah, I know. I've confused myself. No, it's for the red dwarfs, for the M dwarfs. So these are going to hang around for ages, which is great because it means that there's a lot of time for life to arise, should it be able to.
And I mean, presumably that contributes to why there's so many of them. Like
Yes.
they're really common.
Yeah.
Partly because at least they last.
Yeah, they just haven't
keep on
died
going.
yet. Yeah.
Are they also formed at a much higher rate, or is it just simply that they're sticking around?
They are also formed at a higher rate, so they're more likely to form from a collapsing cloud as well. So you got both on your side there. In fact, here's a fun fact. Every star that's ever been born in the entire universe that has a mass less than about 80% the mass of the sun, still alive today.
Wow, really? Because they're just hanging around and they haven't gone through all their fuel yet.
Yeah.
That's amazing.
Cool, wow.
That's wild. Like you think of the universe being really, really, really old, like it's been around effectively forever. And it's things like that make you think, no, they're not. Like other stars have gone through several cycles by now, but the little ones still going.
Yeah.
Like the original ones. That's nuts.
Cool, isn't it? Yeah. So they hang around. So that's great. So all these things coming together, brilliant. Let's
Fantastic.
go find these habitable exoplanets
Sounds
around
perfect.
M dwarfs.
Sounds like the perfect environment for finding habitable exoplanets.
Yeah.
Great. What's the problem?
They're horrible stars.
They're horrible stars. What's the problem? What's the big deal?
Well, it turns out they're very active stars. Now, we talked a little bit about activity a couple of weeks ago when we were talking about the aurora that we were seeing.
Yeah. So the sun's been going through a bit of it's coming into an active period now, and that presents itself to us as, I mean, sunspots and stuff coming off the surface of the sun out into space, which flings itself towards us. And if we pick up some of that in our magnetic fields, and that creates really pretty colors and dancing lights in the sky, that's great. But that's the kind of activity we're talking about.
Yeah.
And if one of those big solar flares from the sun was pointed towards us like that, it'd cause huge problems.
It would.
But fortunately, that's not happening a lot.
No, it's very, very rare.
So the sun's relatively calm.
Yeah.
Good, which is good for us.
Now, these red dwarfs are not calm.
Right.
So you've got to take the solar activity and kind of turn it up to 11.
Okay, right. That seems a little bit counterintuitive to me. I mean, you just said they stick around forever, right? They're cooler. Like stuff's not happening as much down in the core. They're not burning through their fuel as much. Like everything that you've described about a red dwarf sounds like it's just hanging out, doing its thing, not causing trouble, not sticking its head up above the parapet. Like it's just hanging out. So why are they so nasty?
Well, there's a couple of things. First of all, they're very, very nasty when they're born.
Okay.
So they've got extreme magnetic fields when they're formed. And part of this is just to do with their sheer size. So there's a scaling kind of problem where the magnetic fields compared to the size of the star just get kind of out of control.
Right. And as we've discussed on this podcast many times before, anytime you get magnetic fields involved, things just get ugly. Like it's just awful, right? Fun to play with when you're a physicist or an astrophysicist, but hard. But the thing about magnetic fields is if you squash them, then things get ugly. And so is that the thing here, that you've got a smaller star, and so the magnetic fields are just concentrated in a smaller space?
It seems to be, a big part of the problem. Yeah. So there's that. And then there's the actual way that energy makes its way from the core of the star out to the surface. So if you think about stars in a big lineup, right? So we got the most massive stars at one end, the most smaller stars at the other end, there's actually a shift in how energy is transported from the core to the surface. We have two main methods of energy transport that happen in stars. The first one is radiation, radiative transport. So this is just like, your heater is radiating heat towards you. It's a similar kind of concept in photons moving straight through stars. Then there's the other one, which is convection. And convection works just like the convection in a pot on a stove. You get bubbles kind of coming up to the surface. You get churning fields. It's kind of a much more messy, in a way, system.
It's exactly the same as the two kinds of heating that you get in your house from your radiator or, as you said, from your electric heater, right? There's the direct one that you can feel. I can feel the heat coming off that. But over time, the more important part is that the air around the heater warms up and that rises, which draws cooler air up, which then heats up, and you get this huge convective flow around the room. And so those two kinds of heating, really important for your home. And those are the two ones that turn up in stars too, the direct and the convective.
Yeah, exactly. So as you go from the very hottest stars, the very, very hottest stars don't have convection at all. They're just too hot. They're just straight into the universe. That's it. And then as you go down the scale, I'm only talking about surfaces, but you get more and more bigger convective zones in the top of the star. So you come to a star like the sun. The sun has a convective outer layer on the surface and some radiative stuff on the inside. And then you go down and down and down and down all the way to the low mass M dwarfs. Then they're almost fully convective stars. And convection's kind of a problem in a sense when you're talking about activity. Well, it's responsible for activity because now you're physically moving charged particles around on the surface of your star, moving charged particles, magnetic fields. It's just
ugly.
A mess.
Yeah. I could see that. Okay, so because it's a smaller star and because it's much more driven by the actual, bulk motion, the convection of stuff, and a lot of that stuff is charged, and there's magnetic fields, I could see how that would mean that you got then some pretty ugly behavior going on.
Yeah.
Okay.
So you get things like enormous star spots forming, enormous chemical spots, so these are kind of, star spots are sunspots on a star.
So what is that?
Well, those are regions which are slightly cooler than the rest of the surface. And that they're slightly cooler because there's a bit of magnetic field kind of poking through the surface that's drawing the surface layer down, if you like.
Okay.
So there's a spot there. You get chemical spots, which are kind of the magnetic field almost corrals or herds some particular chemical species into a blob on the surface.
Because maybe they're sort of, got multiple charged ions or something or different masses or something like that. So you get these concentrations.
Different chemical elements react differently to magnetic fields.
Yeah.
So,
I never really thought that was possible, but there you go.
Chemical spots. So they're sort of kicking around. And they can be brighter than the rest of the surface because you kind of corralled all the bits into one spot. And then you get, of course, flares and that kind of activity.
And flares are, why do flares happen? I mean, we've sort of talked about a bunch of these things over many podcasts in little bits of detail, but I don't think we've ever really gone there. What is a flare? Why does that happen?
Right. So the plasma on the surface of a star will often follow magnetic field lines. Charged particles like to follow magnetic fields. It's kind of their thing.
Yeah, right? Like the Northern Lights, right? That's charged particles following the Earth's magnetic field down towards the poles and bashing into stuff and causing them to glow.
Yeah. So remember, for these stars, the magnetic field isn't just a kind of a bar magnet, nice and orderly, nice and simple. There's magnetic field lines poking out the surface in all sorts of random directions, doing all sorts of twists and turns and horrible things. It's just it's an utter mess.
It's like one of those squishy stress balls where you squeeze it and then a bit sort of sticks up between your fingers, and pops out in a little bubble. It's that kind of thing. That loads of these pressures suddenly go pop. Here's a bit of magnetic field that just shoots out in a big loop.
Yeah, and the loop is actually the good term. So what happens is you can get a magnetic field line. So the direction of the magnetic field can actually poke up through the surface of the star, do this big arch, and then poke back. I'm doing lovely hand motions here, by the way, so you can follow.
Great for podcasts.
Yeah, exactly. So it pokes up, does a big arch, and then pokes back down into the surface, and that's a loop. And the charged particles on the surface of the star can follow that arch. And these are called prominences. So you get actually plasma flowing off the surface of the star, and we see these on the sun. They're absolutely amazing.
Some of them are enormous.
They're huge, much bigger than the Earth.
Yeah, which is terrifying.
Yeah, and then they sort of, you can imagine this kind of fluid of charged particles going up and onto this loop, and some of the videos that we've got of the sun's prominences, you can actually see some of the plasma get to the top and start raining down because it's the gravitational force is now pulling it back to the surface, and the magnetic field's getting a bit weaker at the top.
That's wild. That's crazy stuff.
It's like raining fire on the sun.
I'll dig one of those out and see if I can put it in the show notes.
They're just gorgeous and very scary at the same time. So you get these prominences, and these are linked to spots as well. So where these prominences exit and enter this solar surface is linked to where the spots form. Now, if you take that idea and you make it a lot bigger,
a lot nastier, yeah.
So what can happen is you get this enormous prominence that can then break. So the top of the loop breaks, and then you get all the stuff just going boof.
So it's getting flung out into space. It's not looping around and raining nicely back down onto the surface. It's going, no, I'm going out.
Yeah.
And I'm going to find something and I'm going to kill it.
Yeah, it's ejected into this enormous flare. So we have flares or coronal mass ejections.
Yeah. And that does happen from the sun.
It does,
right?
yeah.
And if one of those came our way, we'd be in trouble. But fortunately, they're rare enough that the chances of one coming right at us, reasonably slim.
Exactly. And certainly one that's on the kind of scale of that's going to devastate all life on Earth. I mean, we're talking about one in a, I'm pulling numbers here, but I'm not sure, but something like 1 in a 10 billion year event, perhaps.
Yeah. And given that life on Earth has been, from its absolute most basic, about 4.5 billion years, clearly it's at least not common in that kind of time frame. Although I think I remember reading there have been a couple of significant disturbances to life on Earth that are probably from solar mass ejections.
Well, yeah, that's interesting because, we do, when we look at the history of life on Earth, and I'm no evolutionary biologist by any stretch of anyone's imagination.
Come on, Emily, what are you doing with your time?
But, I mean, there's an interesting sort of point that sometimes gets drawn out is that life on Earth has been around for about 3.5 billion years,
right? Okay.
Most of the lifetime of the Earth. In fact, surprisingly quickly, life seems to have just come here. You ready? Okay, bang, here we are.
Give us the environment and we'll do life.
Exactly.
Yeah.
There was no delay.
I mean, and that gives us a really good sense of, well, if that's the way it happens, if we can find the right kind of planets, then there's a good chance we'll find life, which is why we're doing this in the first place.
Yeah, so that seemed to happen very quickly. But complex life, what I believe is termed the Cambrian explosion, only happened a few million years, at 540 million years ago.
So there was, for a really long time,
like
billions of years, there was just the most basic, simple, single-celled stuff just blorping around in the primordial soup. And then the Cambrian explosion was, you know what, we can do better. Let's put a bunch of these things together and create, everything from pterodactyls to wombats. It just went nuts.
So I think there's maybe some idea that the solar variability had an impact on why the life didn't become more complex sooner.
Oh, right. So the sun was nastier in the early days and then settled down a bit. And
I don't think there's any evidence for a single kind of big let's just start again. But maybe it was just kind of this background level of not super nice.
There's too much nastiness coming from the sun. Hold back, everyone. Hold back. Okay, looking good. Let's explode. And that's kind of what happened.
Perhaps.
Maybe. We're hypothesizing. If listeners, if you know more about this than we do, please, get in touch.
So you can imagine that's quite important. Now, if you take a red dwarf star, and in fact, if we take one of our friendliest red dwarf stars, which is the closest star to the sun, so our nearest neighbour.
That'll be one of the Proximas?
Proxima Centauri.
There we are.
Yeah.
It's in the name.
Yeah, exactly. So Proxima Centauri is a little red dwarf star. And if you look at the flare sort of cycles on these stars, turns out that you can get kind of perhaps even life-devastating flares maybe every 1,000,000 years.
Oh, and that's not good because from an evolutionary point of view, 1,000,000 years is nothing.
No.
That's the dinosaurs were, 65 to hundreds of millions of years ago. A 1,000,000 years is nothing.
No. So if you've got something short-circuiting your evolution of life every
we
million
literally
years.
just got going and then, nope, that's it. Don't start again.
Yeah, so that's not super fun.
No.
In fact, one of the brightest flares we've ever seen, in fact, the biggest flare I think we've ever seen from a star, came from Proxima Centauri in 2019. And it was 14,000 times brighter than the entire star. Just one flare.
What?
Yeah.
That's insane. Just so a flare came out and it just went, by the way, we're just 14,000 times brighter than the thing that you're looking at.
Yep.
And that's coming your way.
Yep.
So that's going to really interrupt your attempts at evolution nearby.
Exactly. Yeah. So
Wow.
I mean, even if you're not talking about the direct kind of radiation of like frying life from the photons coming from those flares itself, I mean, obviously these have impacts on things like atmospheres. The Earth's atmosphere is very, very fragile, right? It doesn't take a lot to disrupt it for bad things to happen.
Yeah.
I mean, volcanoes can upset the atmosphere, let alone things from stars.
And we've been pretty lucky in that, the star that we orbit is pretty calm in the grand scheme of things. That's working in our favor. Okay. So I'm beginning to get a sense of why, on the one hand, red dwarfs, there's lots of them. It's great. And the orbits of the planets are closer in, which means they happen faster, which means we can get much more data on them. It's easier to observe that. On the flip side, they're really rubbish for life.
Yeah.
That's
where this new study comes in, because obviously we're trying to look at how stellar variability changes over millennia. Now, I don't know about you, but I don't have millennia to sit around and watch.
Who's got that kind of time?
No,
right?
So it's
things to do.
It's hard. But this new study looked at least over a couple of decades for a bunch of red dwarfs and said, how are they varying on at least this decadal kind of timescale?
Sure. So who's been doing this?
So this is Lucien Mignon and colleagues. So from Grenoble and the French National Centre for Scientific Research.
Okay.
New paper just come out, and they've been looking at 177 red dwarfs that we have spectroscopy or observations of over multiple decades, at least, up to 20 years. And the bottom line of the research was basically the calmest red dwarfs are still much more violent than the sun.
So even the ones which are just the most habitable possibly are still nastier than we've got. Great. Good. Yeah. Excellent.
So that's kind of a thing. Nasty little red dwarfs.
And how does that what's the distribution of that? Like, are they predominantly down the sort of calmer end, or is it sort of more like a bell curve where a few of them are calm, most of them are pretty nasty, and some of them are horrific?
Well, it's interesting because about 75% of the stars in the study showed this long-term variability, and a significant number, so about 12 of them, even showed really complex long-term variability. So what that means is that there's gone some kind of cycle. So we know the sun has this 11-year magnetic field cycle flip, blah, 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 blah. Putting that aside, there seems to be some much larger scale variability on at least the decades, probably into the hundreds of years for many of these stars. Right.
And you can see that even just looking over a 20-year cycle, you can see the evidence for a much longer variability.
Yes, and the complex ones have several periods, so they might have a 100-year timescale and a 20-year timescale or something like that.
Wow.
That makes them really complicated. And that's really important because it's giving us that hint that actually these things are not just variable, that they're really
it's super variable in a not very pleasant way.
Yeah. And
fun to study.
Oh, absolutely.
If you're a Red Dwarf astronomer, that's cool.
Fascinating. So it's nice to see those things changing on these timescales, but you can try and then infer what the Red Dwarf, how it would flare and change in its variability over millennia, from at least starting from the decadal kind of timescale.
How has this study been done? What have they been using to look at these? Because it's going over several decades. So what instruments have they been observing with?
Well, we've got HARPS, which I think we've mentioned HARPS before.
HARPS rings a vague bell. Remind me.
HARPS is one of our favourite spectrographs.
In the list of spectrographs, this one's up there.
It's one of the most famous ones, to be fair. So HARPS stands for High Accuracy Radial Velocity Planet Searcher.
Yes, okay.
So it's famous for planet hunting, right? So one of the techniques that we use to find planets is looking at the redshift and blue shift of a star as it's wobbling towards and away from us. And we measure that using a spectrograph.
Right, and it's wobbling because the planet's going around it. And so that entire system, even though the star is much bigger, the star is still, they're both orbiting around a common center of mass, which means as the planet goes around, the star's also going around, just this little wobble. And so a bit of the wobble's towards us, a bit of the wobble's away from us. You see the blue shift and the red shift, and you can infer the planet from that, which is cool. So HARPS is where? Is what? Is it a telescope? Like what is it?
It's a spectrograph on a telescope.
Right, okay.
It's on a 4-meter telescope, so it's fairly modest, but the spectrograph it's famous. It's one of the most high precision spectrographs we've got in the world, and it's discovered loads of exoplanets. It's right up there.
Okay.
It's one of the famous kingpins, really.
Okay. I'll put that into the category of things that I probably ought to have paid more attention to over time.
It's fine. Maybe it's one of these things that you just know because you know. So HARPS has got a massive back catalogue of data, right? And most of that data are public. And so you can go back and have a look at observations that HARPS did in 2003, for example, the spectra that it took. And that's kind of what the study did. It went back and looked over the whole, from 2003 to 2019. Let's pull out all the red dwarf spectra. Some of them have got lots of observations over that kind of 20-ish year time frame. And let's just have a look at the variability and how that's changed over that time frame. And to look at variability, we've got some clues that we can pick up in spectra itself. So a spectrum, if you remember, we're taking the light from the star, we're breaking it up into its wavelengths. Like when you have a prism in the sun, you get the rainbow. It's just a very fancy, big version of that.
Fancy version of a rainbow. Yeah,
exactly. And what we're looking for in a spectrum is we're looking for chemical fingerprints from different atomic species or chemical elements. So there's gaps in that rainbow, which are caused by the fact that there's chemical elements, say, on the surface of the star. And there's some really important ones that we can look at for stellar variability. So there's calcium. Calcium has 2 lines called H and K, which are really, really useful to look at. We look at the sodium doublet, a very famous set of 2 lines of sodium in the yellow. And we look at hydrogen alpha, which is a very red kind of part of the spectrum. So
right.
If you're a chemist or if you like chemical elements, those are the ones that we like to look at because they are influenced by changes in the magnetic field. So the amount of gap or indeed sometimes the amount of emission extra that you find in this part of the spectrum is dependent on the amount of activity.
Right, yeah. I mean, I hadn't really thought about that, but that kind of makes sense, that all of these lines, these fingerprints in the spectra that you're talking about for these different elements are affected by whether or not there are stonking great magnetic fields nearby. The reason those lines are there is because these different chemical elements or molecules have electrons whizzing around, and those electrons are affected by magnetic fields, which means the fingerprint itself depends on whether or not there's a really strong magnetic field nearby.
Yeah. So they're affected by magnetic fields, absolutely. They're also affected by spots because spots change they change the surface of the star. Actually, spots can look a lot like pulsations, the ones that I study, if you're not careful and make sure you know what you're looking at, because they can change the Doppler shifts that you're looking at. So spots can change them. Chemical spots are obvious, right? If you get a lump of sodium over there, then hey,
you'll see that.
That's going to change your sodium.
Because there's a lot of sodium lines.
Exactly.
Yeah.
Yeah. So there's all sorts of changes that reflect the changing magnetic field and reflect the changing activity of the star. You can also look at just, your bulk standard brightness of the star, what we call the photometry, and say, well, okay, it's a little bit brighter at the moment, it's a little bit fainter at the moment. So that's also an indicator of activity.
Right. On the large scale, it's brighter, it's dimmer. Yeah.
So those are our measurements for the variability of the star. And what's actually, we sort of just hinted at it, what's really important to understand also with this variability is that if you're looking at those radial velocities, if you're looking at HARPS trying to measure a planet around a red dwarf, then you need to understand the activity so that you don't mistake the activity for a planet.
Yeah.
Right?
Yeah. Particularly as, if the planet whizzes by and then you don't get to see it again until the next time it whizzes by, there's a lot of things that could look like a planet whizzing by once.
Yeah, and it all can just affect your observations generally.
Yeah.
So both have happened where actually, we've detected planets, quote unquote, that turned out to be just
not a planet.
Yeah, star spots or other kinds of activity, or we've calculated how much the star is wobbling just because we weren't accounting for the activity. So both of those things need to be very carefully dealt with.
Turns out spotting a planet around a very distant star that's going crazy itself, it's not an easy thing to do.
No, they're not the easiest targets in the world. I'll give you that. Yeah, so all of this stuff, so there's, in terms of the importance of the study, that's really important to understanding the radial velocities. But then, of course, we've got that larger question of, are these things going to actually be habitable at all?
Yeah, I mean, that's kind of where we're led around to, isn't it? I mean, you started at the beginning with this paradox, and am I right in saying that like summing up the paradox, on the one hand, red dwarfs are perfect place to go and look for habitable planets for all the reasons we've discussed. On the other hand, they are the worst places to be looking for habitable planets because they would just destroy life within a million years, even if it did get going. That's the paradox. Is red dwarfs great? Red dwarfs are the worst. So do we just abandon all hope then on finding habitable life around red dwarfs?
Well, it's interesting. So there's a few more things that we want to kind of find out, I think, to really be able to say emphatically, yeah, no, we're just going to, they're not great.
Not going to happen.
Let's just not. Let's just not. We need to understand atmospheres a lot better because, I mean, there are some possibilities that atmospheres can protect you from harsh things coming from your host star. The atmosphere of the Earth protects us from ultraviolet radiation from the sun.
It does a really good job.
Yeah. So
I wouldn't want to push that too hard, though.
Well, no. So, but we don't understand what happens if you have a different kind of atmosphere. So it's important to try and measure atmospheres, chemical compositions of atmospheres, and then try and figure out what would happen if you shoved one of these flares onto a complex atmosphere. Maybe it's okay. Maybe.
Really hard to then extrapolate from that to, okay, so maybe that kind of atmosphere would be able to cope with a really nasty star nearby and therefore, I don't know, life? Is that possible?
Possible, yeah. But it's good to understand at least what might be happening. Another factor which we haven't even touched on before is that what happens when you have old systems. So these are red dwarfs have been around for billions of years. With close planets, is that they tend to get tidally locked.
Like the moon around the Earth,
Yep.
You get these tidal forces that pull on a bit of, in our case, the moon pulls it a bit this way, pulls it a bit that way. And over long periods of time, you end up with the same bit of the moon facing the Earth all the time. And that can happen with planets too, if they're close in.
Yeah, we've got loads of them that we know are tidally locked. I mean, the TRAPPIST system, probably one of the most famous ones.
Right.
They're all tidally locked.
None of them in our solar system, like Mercury's not. It's
Mercury's
not
on
enough.
the way.
Is it?
Yeah, so Mercury's in a resonance at the moment in its orbit. I think it's a 2 to 3 resonance. So it spins twice for every 3 times it goes round, or vice versa.
Right. And so is that going to, over time,
It will
turn into tidally locked?
Yeah.
Oh.
Well, everything will eventually.
Right.
Run the universe for long
given
enough.
infinite time frames, yeah.
Yeah,
okay.
exactly. Assuming the sun's still there, but that's a different problem.
All other things being equal, it will happen to us.
Yeah. So, tidally locked. Now, does it help or hinder you? That's a question. So, tidal locking probably causes nasty things in the atmosphere because you're heating one half of the atmosphere, but not the other half, which probably generates huge winds, for example.
Yeah.
That's not very fun. But maybe it means you can live on the other side of the planet, away from the flares.
In perpetual darkness and really windiness, but maybe. I mean, who knows? We've never tried this.
No, exactly.
Could be great.
Yeah.
If you're a night owl who likes wind.
So, there's it's not completely out of the question.
Sure. I mean, this does sound like a little bit of a playground for the theoretical evolutionary biologists that, come on, let's just make some models, see what happens.
Yeah. Well, the good news is it might not be theoretical forever.
Right.
So we've got a fancy space telescope
Yes,
that's helping us here.
We do.
We have James Webb,
Yes.
who currently to date has spent about a quarter of its time studying exoplanets.
Cool.
Cool fact.
Very nice.
So it is part of its huge science mission, which includes just look at everything.
Everything, do all the things.
Is exoplanet
Yeah.
science.
I mean, that was one of its big selling points, wasn't it?
Exactly. And of course, it's tailored to look at these red dwarfs because red dwarfs, very red, infrared, it's all...
That's what JWST does.
Exactly.
Yeah.
So JWST is not a planet hunter, right? That's quite important. It's not out there to go and find hundreds and hundreds of exoplanets. That's a job for other telescopes.
Right. It's more of a specialist that when we want to have a look at this system really, really well, let's get JWST onto it.
Yeah. So it might find the odd one just from doing other stuff.
Accidentally.
But it's not...
Stumble over an exoplanet.
Main goal, yeah. So James Webb is trying to do in exoplanets that's beyond what we've ever been able to do before with these red dwarfs is really study the atmospheres in very, very high detail. So what we do is we wait for one of these planets that's going around a red dwarf to go in front of its host star, and we look at the spectrum of what that star looks like when the planet is in front of it. And then we wait. And we wait till the planet's not in front of it. Or maybe we do it the other way around. Whatever.
Whichever, yeah.
So we get a spectrum of star, and then we get a spectrum of star plus planet.
Right.
And then we can say, hey, that stuff that wasn't in star alone, but is in star plus planet, that is planet.
That must be planet.
Yeah.
Which makes sense. Yeah.
So it's called transmission spectroscopy. You can do several different ways, but that's kind of the main way. And James Webb is built to do this.
Right. So presumably it can start picking up all sorts of information about like what's on that planet. Not just that it's there, but what's it made of, what's in its atmosphere. Because when the light's coming from the star through the atmosphere of the planet, you're going to lose some of it because it gets absorbed. It excites some of the molecules and they start radiating in different ways. And so you're going to see different signatures of the stuff that is there.
Yeah.
Which is awesome.
So it's very,
we have done this before, right?
Yeah,
not in the same kind of precision and detail.
HARPS does it fairly regularly, for example.
Okay.
But it's just now we've got a dedicated space telescope that loves the infrared that can do this
and
very, very well.
And is really good at it.
Yeah.
Wow.
Exactly.
Cool.
So that will help, I think. That will tell us a lot more about atmospheres, and maybe that will help answer the question of, are we actually going to be able to find anything habitable around these red dwarfs?
Because we're looking for what? Like, what are the sorts of markers that would say, oh, actually, there's something really interesting happening there?
It's a good question. I think I'm not very good at atmospheres, but
taking you out of your comfort zone.
Yeah, definitely. My naive hypothesis would be you're looking for thick atmospheres that offer you some shielding. You're looking for chemical species, whatever they are, that are very good at absorbing up your ultraviolet for the flares.
Right. Yeah.
Things that aren't too nasty. I don't know, not second Venuses. That's probably not super helpful.
Maybe not an enormous amount of hydrochloric acid.
But you don't want to be too thin because then you're not like Mars. Mars is way too thin.
Yeah.
So.
And the thickness of the atmosphere would come out as, there's a really strong chemical signature coming through there. Like we can see a lot of that as opposed to a really weak one, which would say there's not a lot of atmosphere there.
Yeah. Maybe lots of nice molecules.
Yeah.
We don't have any biomarkers per se that you can say, there's life there because we saw some particular hydrocarbon.
Yeah, hydrocarbon, therefore wombats. Like it doesn't work that way.
No, we don't have one yet.
Yeah.
Well, maybe we will one day, but
you can look at least for the signature of things which we see in our atmosphere, which you don't necessarily see in other atmospheres in the solar system. And I'm guessing that would be certain organic chemical molecules.
Yep, bit of water would be nice.
Water, yeah.
That's always good.
Yeah,
so,
various hydrocarbons. Yeah.
So there's hope, I would say. But in some ways, I always thought that one of the best kept secrets about James Webb is that it's not Hubble.
It seems a fairly obvious statement, but explain that. What does that mean?
I mean, there was a lot of talk about how it's the next generation Hubble. And in a way it is.
Sure. It's a space telescope and it's really good.
But it's an infrared version of Hubble, right? And that is significant. That does change. But and we are getting beautiful pictures off James Webb, and I suspect that that's part of its charm, but it's not quite a Hubble in that sense. It's not designed to see as the human eye sees.
Right.
It's designed to see much more in this infrared part of the spectrum.
Yeah, so that's more the marketing side is, yes, okay, we can give you the beautiful pictures, but that's not the point.
Yeah, and I think the second part of that, the best kept secret of the exoplanet hunt with James Webb, or the exoplanet kind of science that James Webb's going to be doing, is that, we can do wonderful exoplanet science on these M dwarfs, but they may not actually be habitable at all.
We can do it if you wanna, but don't get too excited.
So Parker, I think all the ideas of finding the Earth twin, some people say that's about a decade away still.
Right.
I'm not sure. Maybe I think we can be maybe a bit more optimistic. I think we'll maybe find one in the next few years, but hey, at least we'll know whether or not these M dwarfs are habitable much sooner than that, I suspect.
Well, that brings us to the end of another episode of the Syzygy podcast. Emily, I don't know. On the one hand, you got me really excited there for a moment because we got loads of red dwarfs and we can study them really, really well, and we've got a stonking new space telescope that's going to be able to look at them because they're red and it does red and infrared really, really well. And then you tell me, no, they're really nasty stars, and the chances of finding life on them nearby is just really, really small. But hey, look, everything that we can do to study different systems will lead us closer to being able to answer this really big question, which is it just us or is there other? And maybe we're going to have to come back and revisit that question in a future episode.
Absolutely. Isn't it amazing how it's a question that just one observation, just one data point could completely change the world? Yeah.
One of the rovers up on Mars turns over a rock and goes, oh, look, it's a mushroom, and well, that's done. We're done now. We've answered that one. It's literally next door. Or even just finding evidence that there was, it would be, and we've talked about this before, it would be huge, and yet at the same time would change almost nothing. It's one of those weird shifts. Anyway, we can revisit that one. Listen, if you're at home and wondering how you could possibly get in touch with us in order to correct some of the evolutionary biology that we've been nattering on about today, knowing literally nothing about that subject, and you want to set us straight, Emily, how can people get in touch with us here at Syzygy?
Well, I'm going to change the order here because I'm going to put what I think is our best bit of information out on the web first.
Yep.
Go to syzygy.fm.
The website. Yes.
syzygy.fm. I'm always looking at it going, that's a really pretty website. I'm really glad you did that, Chris.
You need to get out more, though, I think, Emily. I think that's part of the problem here. Yes, go to syzygy.fm, and there you can find not only this episode and all of the other episodes, going back to episode dot, with all of the links and all the pretty pictures and everything. But there's also a contact page where you can put in your details and send us a little message, and we'll receive that and go, great, thanks, that's awesome. It also has a page dedicated to thanking all of the people who have supported us here on the show. So if you want to be one of those, you can head over to patreon.com/syzygypod and become a financial supporter of the show and help us to keep the electrons flowing through said website, as well as supporting all the other things we do, like buying Emily a new microphone, which we finally got set up and working. But if people wanted to find us elsewhere on the web, where can they do that?
So Facebook, next thing. I know what a Facebook is. I understand the Facebook.
You are of the generation that Facebook's.
I am, yes. So you can chuck in the SYZYGY tag. You'll find a page that looks the same. It's got the logo.
You'll
all
know
lovely.
us when you find us. It's not too hard.
Yeah. And if you're gramming, then I'll try and figure out how to get things onto the Instagram.
If you're all about the Insta, then you can find us on Insta at syzygypod, which is where we are in most places on the
internet.
And you
don't get photos of our dinner. You get nice things about the universe.
That's right. We don't Instagram our dinner. We Instagram red dwarf stars instead, which is much, much more interesting. I tell you, astronomical Instagram is pretty awesome. There's some really cool stuff there.
There's too much in the universe, isn't there?
Yeah,
there's just too much. There's too much prettiness.
Yeah.
You could just look at the Instagram of just Jupiter forever and be happy.
It does make me wonder why we're doing this in an audio format. But hey, look, this whatever works. Listen, I mentioned one way that you can support the show, but of course the biggest way that you can support the show is by telling everyone that you know. If there's someone in your life who would really benefit from hearing more about the wonderful world of astronomy, cosmology, astrophysics, the universe, then point them in the direction of the Syzygy podcast, because the more people that hear about us, the bigger our audience gets, and we feel like we're doing a useful thing for the world. So just spread the word. Get onto your podcast player of choice, your podcast directory of choice, and give us a review, give us some stars, put some words in there telling the world how cool we are, because that also helps us to rise up through the noise and helps other people to find us. But otherwise, we should just probably move on. We've managed to do 3 in a row now.
Yeah, I'm going to break that now, I'm afraid.
Yeah, Emily's heading overseas for a bit.
Actually having a holiday.
Which is really nice. So she's off for a couple of weeks. And so we'll take a couple of weeks break, and you will hear from us again when Emily's back sometime in we'll be into April by then.
We will.
Yeah. So until then, dear listeners, we'll catch you soon. Bye-bye.
See you later. To me, it just reinforces my incredibly unpopular opinion, by the way, that I don't reckon there's other life out there.
Ooh.
Because
That's a big call.
I know, but...
Really?
Well...
Wow, that's a whole other
very
episode.
Unpopular opinion, but...
That's a whole other episode. We might have to dig into that one.
Chances, every time you look, it's just like, nope, you can't have life over there. Nope, that's not going to work. Nope. You need to have a sun-like star, an Earth-like planet. It needs to be exactly the same age as Earth. It's getting...
But surely the statistics
hard.
are against you on this one.
Well...
Like nothing? Nowhere?
I don't know if they are. I think we need to look at those statistics. Because how many Earth-like planets are there around sun-like stars that are the right age and the right part of their galaxies and the right time and the right chemical composition? And it's feeling very...
I think we might need to come back and explore that one in another episode.